Thank you for your participation today. We now begin the second installment of RICOH THETA times IoT Developers Contest Cloud API Seminar. We will explain the topics shown in the slides. All materials used in this seminar are released to the public at the URLs shown on this slide. Especially for those of you watching this seminar through the Nico Live broadcast, the text on the slides may be difficult to read. You can view the materials on SlideShare while watching the broadcast. First, Takakua of RICOH will give the overview of Cloud API. RICOH Cloud API is an interface available from programs which run on PCs, smartphones, tablets, and single-board computers. API provided by RICOH. Image processing, video communication, photo and media storage, remote control, authentication, authorization. These are provided as free beta versions available to any contestant. There are available resources to the developers as follows: Cloud API, SDK, sample programs. These are published in the GitHub URL. These can be accessed by people who have not registered as contestants too. You need some other things before using these resources in advance. These are explained now. First, the client credential. API server needs this to identify the application. Client ID and client secret comprise user credential. Another is a user account. Cloud API server needs this to identify the user. In this case, user ID and password comprise user credential. We skip the explanation of how to obtain these. It was explained in the previous seminar. Please see the page 8 to 9 of the previous seminar slides for details. We now move on to the introduction of Cloud API functions. I would like to give you an overview of one of the newly provided functions. We have been offering a service called Media Storage that allows you to store and view images. Today, we are introducing a new API and service for image processing. We call it Image Processing Service. You can perform image processing on the images stored in Media Storage Service by using this API. Provided API is very simple. You specify an ID on the media storage and the filter which you intend to invoke. This time, we provide smoothing of histogram, grayscale, and reduction of image size. In the case of the reduction of image size, you specify the width and height as well. As the response, the ID of the media storage where the processed image is stored is returned. You can perform image processing easily on the cloud using this API. Now let me explain the effect of each image processing function. First is the smoothing of histogram. This process allows you to enhance the image to make it bright and clear. For example, you might have an image where some people's faces appear darker than others due to the amount of light or position of the light source. You can enhance such images using this filtering function. Second is the grayscale. You can change the original image to a monochrome image. This will be a fun tool to play with, giving your picture a totally different impression. Third is the image size reduction. Although the images taken with Theta S are now much clearer, this means that the sizes of these images are much larger. This filtering function allows you to reduce the image size, thus reducing the load during subsequent processing. For instance, when you convert the image into 1/2 by 1/2, the image size will be reduced to approximately 1/3 of the original. If you don't change the horizontal to vertical ratio, the image can be replayed in the viewer. Of course, you may want to closely look at a high-resolution image in some cases, but this function can be used for other cases where you want to reduce the image size for purposes such as time-lapse replay or using the image as a thumbnail. Hello, I'm Eiji Hosono from RICOH. I will give you an introduction on the Media Storage API. Here, I will focus mainly on the contents that were updated since the last seminar. At the first installment of the API seminar held in May, we provided a slideshow application that we had created. This sample slideshow application is featured with all available functions, including cloud support, multi-user, and multi-platform. This application was created using HTML, CSS, and JavaScript, with a total of about 100 lines of code. This time, we have implemented a new feature you've been waiting for, namely the user-defined metadata and search function. We have added user-defined metadata and search function. You can add metadata to the images in the cloud. Metadata is a pair of strings in the format opening brace, key string, column, value string, closing brace. We can define up to 10 metadata pairs per image. You can search images using metadata as the search key. These metadata cover many attributes including favorite, like, rating, and comment. Here are some examples of attributes as user-defined metadata in key-value pair format. The related APIs SDKs are shown in the table. Since SDKs are provided, application development is a piece of cake. So, we've created another application for this second installment of the seminar. A sample slideshow application that supports your favorite. You can mark an image as your favorite using the Your Favorite button. You can select the images to be used for the slideshow from All Photos or My Favorites using search filtering. This application was created using HTML, CSS, and JavaScript, with a total of about 100 lines of code, just like the sample application introduced at the last seminar. This slide shows the overall configuration of the demo shown today. The storage server and authentication server are placed on the cloud side. The application runs in a browser on the client PC side. You will need to have a local server that runs on the client PC side in order to distribute application contents. In this configuration, the application will perform the 3 steps shown in the figure. Application contents are distributed from the local server on the PC. When you open the URL of the local host in your browser, the browser loads the contents, and the application starts up. After the application starts up, you can make the application collaborate with the cloud services using the JavaScript version SDK. So, here's the demo you've been waiting for. Let's start the application. Let's start the slideshow. Let's mark some images as your favorite. Let's check that the mark is displayed on the next turn. Let's change the search filtering to My Favorites. Start the slideshow. Check that the slideshow only displays those images you selected as My Favorites. Change the search filtering to All Photos. From your smartphone, mark some images as your favorite. Check that the markings are reflected in the slideshow running on the browser side. I will continue explaining the source code. As shown here, user-defined metadata is added/deleted when Your Favorite button is pressed. As shown here, you can check the status of user-defined metadata settings when the image is updated. As shown here, you can apply search conditions to the filter when you obtain the list of image data. And that is all for the source code. That is all for what has been updated in the Media Storage API. User-defined metadata and search function is very easy to use. You can utilize these functions in many ways. Thank you. Hello, I'm going to give you an introduction on the video communication function using RICOH Theta S. Here is the table of contents. First, I will give you an overview on the sample applications for video communication, which have been created by RICOH and released to the public. Then, I will perform a demo to show you how the applications actually work. After the demo, I will explain about the configuration of the sample applications and give you a summary at the end. We have created sample applications for video communication and made them available through GitHub. There are two sample applications. Sample 1 is an application to perform video chat between two PCs with the RICOH Theta S connected. Sample 2 is an application that was just released yesterday. This application performs video streaming for RICOH Theta S to devices such as PCs from a single-board computer, which is a small computer that costs only a few thousand yen. First, I will give you an overview of Sample 1. As shown in the figure, Sample 1 performs video chat between two PCs using a function called WebRTC, provided by the browser. To simply explain how WebRTC works, each PC will connect to the RICOH server and perform a process called signaling to exchange information such as IP addresses and ports. After the PCs have identified each other, where they have been connected to, through signaling, they will be able to start a video chat. Next is the overview of Sample 2. As shown in the figure, Sample 2 performs video streaming from a single-board computer to other PCs, etc. Just like Sample 1, this application also uses the browser's WebRTC function. Today, I'm going to show you a demo of Sample 2 for video streaming distribution. So let me first explain the procedures to run this sample application. On the distributor side, you must build and configure scripts, etc. in advance. We won't have enough time today to demonstrate how to perform all of these procedures, but you can access GitHub to see the procedures in detail. Next, start RICOH Theta S in live streaming mode and connect it to the single-board computer. To start in live streaming mode, start while pressing the shooting mode button on RICOH Theta S. Then, execute the script. The single-board computer enters wait state and will be ready for use. On the viewer side, you must also build and configure scripts, etc. in advance, just as you did on the distributor side. Open the HTML page in the browser. Log in and connect to the distributor side ID to start viewing. You must press the log off button to quit. If you do not correctly complete this quit process by pressing the log off button, the disconnection may not be correctly notified to the distributor side, and video streaming may continue. So, here is the demo for video streaming distribution. On the left, the PC's browser where you watch the video is displayed. On the right, the screen of the single-board computer that streams the video is displayed. We have already run npm start command on the Raspberry Pi, and it's in the wait state. You can see the log that shows that the connection is now established. So it's in a wait state after it was connected to RICOH's signaling server. Now let's log in from the web browser on the viewer side. I've already entered an ID with Theta that was set up on the Raspberry Pi side. When I push the connect button, you can see the movie. Theta S makes two fisheye lens images available side by side in live streaming mode. It's called double fisheye format. This format is difficult for people to understand. So, the sample application offers the so-called Theta view. When you push this button, you can see the 360-degree panoramic view as you can see with the Theta application. Pressing the log out button disconnects you. This concludes the short demo. Next, I will explain about the configuration of sample application 2 that was used in the demo I've just shown you. On the server side, there are two functions, auth and signaling. The auth function performs user authentication authorization for the distributor and viewer sides. The signaling function relays between users any information obtained through signaling that I have explained in a previous slide. In order to access from a web browser, an HTTP-based protocol called XMPP over BOSH is used. The viewer side is configured with a web browser, open source library, and code created by RICOH. As the open source library, WebRTC and BOSH libraries are used. The distributor side is configured almost in the same way as the viewer side. The only difference is that the browser is operated in an environment without any GUI and from a program using a library called Selenium WebDriver. Here is the summary. As we have shown through the demo, you can perform video streaming for RICOH Theta S using RICOH's signaling server and WebRTC. Video streaming can also be performed from a single-board computer. Video viewing is possible on PCs, Android smartphones, etc. Although we only showed video viewing on a single PC, the program allows viewing on multiple devices as well. This is all for the introduction of the video communication function. Good evening, everyone. I'm Hiroshi Suito from RICOH. I'm going to give you an introduction on the Remote Control Service, a new cloud service that we started offering in June. Here is the table of contents. First, I will explain what Remote Control Service is, what you can accomplish with this service, and the procedures to use it. Next, I will explain about the sample program released through GitHub and how to use it. Then, I will perform a demo to show you how the program actually operates. So, let's begin. On this slide, the figure shows the services offered by Remote Control. This service allows messaging among multiple computers. This means that you will be able to operate RICOH Theta S from a remote computer. MQTT, a lightweight messaging protocol for the IoT, is used for the communication among computers. This protocol is used along with the authentication service provided by RICOH so that you can safely and easily use this service. Let's go on to the next slide. This slide shows the overview of the provided system. First, there are two supported languages, Python and JavaScript. The Python version and JavaScript version both provide much of the same basic functions. The only difference is the supported communication protocol. Both versions support encryption for the communication channel. Protection against data snooping is provided, so secure messaging is achieved. The JavaScript version supports WebSocket as the communication protocol allowing for secure communication. Next, I will explain the specifications of access control for messaging. Currently, the specification allows messaging only between a fixed set of user IDs. In this case, the user ID is the user account set up for this developers contest. The figure on the slide shows the communication protocols that I have just explained and the relationship with the released sample libraries. Let's move on to the next slide. Here, I will explain about the procedures to use the Python version of the library. They can be grouped into three major steps. The first step is to install the authentication library and remote control application. The second step is to download the intermediate certificate. The third step is to configure client credentials. The intermediate certificate is required to encrypt the message communication channel. To configure credentials, go to the samples directory in the downloaded application. Rename the file config-template.json to config.json. In the config.json file, add the client credential, user account, and the path to the certificate. You will be able to use the sample program when you complete these procedures. I will move on to the next section to explain the library and sample program. This slide shows you the class and class methods used for remote control. From here on, the side that instructs or sends the command for the shooting operation from a remote device will be called the shooter side, and the side that is connected to the theta S to perform the actual shooting will be called the device side. Now, let's take a look at the table. First is the constructor. In the library, there's a class called client. You must specify the client ID and client secret to it. Next are the class methods. The first method, connect, is used to connect the computer to the cloud server. Both the shooter side and device side will be using this method. As arguments, you must specify the user ID, password, and the path of the certificate. The second method, listen, is used on the device side to set the system in the wait for shooting state. As arguments, you must specify the device ID and callback functions to be executed when the shooting command is received. I will explain this in a little more detail later on. The third method, shoot, is used on the shooter side to send the shooting command. These three methods are the basic methods used in the remote control application. There are other methods that can be used to disconnect from the server, release from the wait for shooting state, and send-receive general messages. Let's move on to the next slide. On this slide, you can take a look at the actual source code of the sample program while I explain how to use these methods. First, you will import the client class that I have explained on the previous slide. In RICOH API, this class is provided in the client package of camera control. In the code on the shooter side, the instance camera is created using the client class constructor. Then, the connect method is invoked to connect to the server. When the connection is established, the shoot method is used on the shooter side to send the shooting command to the device specified with the device ID. In this case, the device ID is a user-specified arbitrary string. For the device ID, you can use up to 32 characters including uppercase, lowercase, alphanumeric characters, and underscore. Next is the procedure on the device side. The same procedure used on the shooter side to connect to the server is used on the device side. Then, the listen method is used to set the device specified with the ID argument in the wait for shooting state. The callback function that the system executes when the shooting command is received is also specified. The format of the callback function will be explained along with how to use the sample application. At the bottom of this slide are several important points that you should follow. So I hope you come back and check these later when you start using the application. Now I'm going to explain how to actually use this sample application using the execution example 1 in the slide. In this sample application, you will specify the optional parameter and command from the command line interpreter to execute a Python script. Two options are provided. The D option specifies the device ID, and P option specifies the parameter. Two commands are provided. The start command is used to put the system in wait for shooting state, and the shoot command to send the shooting command. In execution example 1, theta is entered as the device ID, and the shoot command is executed with no parameters. On the device side, again, theta is entered as the device ID, and the start command is executed to put the system in wait for shooting mode. When the shoot command is received on the device side while in this waiting state, the output should look like the one on the slide. The first three parameters are those sent from the shooter side. The last parameter, fun_param, indicates the parameter for the callback function. In execution example 2, the shooter side has specified the associated parameters using the P option when the shooting command was sent. So these parameters are also sent to the device side. In the next slide, I will explain about the callback function that is executed when these parameters are received. This slide shows the code implemented on the device side. On the third line, you can see the listen method. The arguments to it are the device ID, and additionally a callback function and its argument of type tuple. In this example, the callback function onReceive is specified. This function consists of three mandatory parameters that are set by the system and option parameters that the developer can specify. The mandatory parameters consist of the device ID, command type, and associated information parameters sent from the shooter side. The number of option parameters should be adjusted to match the number of elements specified for the argument fargs in the listen method. In this example, a string object callback args is specified. Therefore, the number of arguments is 4 in total, including the 3 mandatory parameters. If you do not specify anything for fargs, then the number of arguments is 3, just the 3 mandatory parameters. At the bottom of this slide are several important points that you should note. I recommend you come back and read these carefully. The last thing I would like to explain is the API related to shooting. RICOH Theta S is compatible to Google's Open Spherical Camera, OSC, API version 1.0. The OSC API controls spherical cameras, including the RICOH Theta S. This table shows the class methods used to control RICOH Theta S from Python programs using the OSC. This library is packaged with the sample program, so I encourage you to try it out. Let's go on to the next slide. I will execute the sample program to show you how it actually operates. To keep the configuration simple, I am using a single PC to execute both the shooter side and the device side, as shown in the figure. First, you must prepare 2 network interface cards, NICs, for the device side. One of them is used for a wireless connection to Theta S, and the other is used to connect to the internet. Note that some PCs are only equipped with one wireless LAN adapter. Beware. When you connect the Theta S, the serial number printed on the Theta S is used as the SSID and initial password. Keep the wireless mode on Theta S enabled while you connect it to the computer. So, let me make some adjustments and prepare for the demo. This short demo is meant to explain the basic operation of the sample application. As I explained earlier, one PC runs both functions of shooter side and device side in this demo. This left-hand side shows the shooter side, and the right-hand side shows the device side. First, I will run the start command to make the system wait in a state that is ready to shoot a photo. There's a script called remocon.py in the sample directory. Let's specify theta using the D option to this script and invoke the start command. It takes a little while, but we now see the log that says connecting. The system is now ready to shoot a photo. On the shooter side, let's invoke the shoot command by specifying theta using the D option, but without specifying additional parameters. You can see that theta has captured a photo. The information on the shooter side is passed to the device side. Device ID and the type of command are passed. There is no additional parameter. Now let's try again, this time with the P option to specify parameters. I use the parameters to set the shutter speed at 1.0 and ISO at 200. The device side receives the shutter speed and ISO. I can now capture the photo with this manual setting, so to speak. Shutter speed of 1.0 means 1 second exposure. So you hear a slightly different shutter sound with this long exposure. This is a rather simple demo. I shall note that by using the Shoot API that was explained earlier, you can transfer the images captured by Theta to computers, or use the media storage to manage your photos. Okay, now let me go back to the slides. This slide shows how to coordinate the remote control function with media storage. This example can be applied to cases in which you want to take images with the remote control function and manage them with media storage. We also have some sample codes on the following slides for reference. This concludes the introduction of the remote control function.